Hi, good afternoon, everyone. I'm going to wait for a few minutes to see if others are joining, and then we'll get started. All right, good afternoon. I hope you can hear me and see the screen. Can you please confirm if you can? All right. So in the last few lectures, we are talking about water resources and why do we need to plan and manage water resources. And these water resources, we try to put in the context of a system and how do we analyze these water resources as systems. And in this process, we have seen how to optimize a function. And we began with looking at how do we determine a minimum and maximum values for a function. And we also looked at how do we optimize a given function with one variable or two variables or multiple variables. Followed by that, we looked at how do we optimize a function given that we have some constraints. So in this scenario, for example, we are looking at a particular example where we are interested to calculate what is the area of the crops required so that the benefits that we get from the crops is maximum. So we have been talking about this example for the past few lectures. Just to recap here, we have two crops, crop 1 and crop 2. And when somebody wants to grow these crops, crop 1 and crop 2, they have certain constraints. For example, the total amount of money they have is limited. The total amount of land available is limited. And based on these two constraints, we have to provide a solution such that the benefit or the profit is maximum when we grow these two crops. And these conditions, whatever you are seeing in the problem, we try to convert them into mathematical equations. And those equations are, so Z is the benefit that we want to get from the crops, X1 and X2, or the area of the crops. And here we have a factor 2 because the benefit that we get from crop 1 is 2 rupees per hectare, for example. And the benefit that we get from crop 2 is 1 rupee per hectare. So we have the factor 2 times x1 plus 1 times x2. So this is the benefit or the profit that we want to maximize. And to maximize this, we also have constraints such that the total area of the crops is only 200 hectares. So the sum of the total crops, crop 1 and crop 2, can only be grown in a total area of 200 hectares. And the total amount of money that is available is only 300 rupees or 300 units. And at any given point of time, the area of crop 1 and area of crop 2 can only be either 0 or positive. It cannot be negative. So these are the constraints that we have. And we also saw an example how to solve a problem or how to optimize the function when we have multiple variables x1 and x2 and we have multiple constraints. For example, in this example that we saw, it is an equation x1 square plus x2 square minus 4x1 minus 4x2 plus 8, which we need to optimize for the two given constraints here, g1 and g2. And the process that we followed was to first convert the inequalities into equality. So for G1, we have more than or equal to 0 as an inequality. And for G2, we have it as less than or equal to 5. So these are the two inequalities that we need to convert into equalities. And to do so, what we did was, if it is more than or equal to 0, then what we can do is simply to take a negative of this function, whole function, and then add plus s1 square. And similarly here what we did was, for this function, when we add certain value, then that becomes equals to 0. So the inequality we are converting into equality. And then we also applied Lagrangian multiplier method, where the f of x is now converted into a Lagrangian function, Lagrangian f of x, by simply subtracting f of x minus lambda 1 g1 of x, which is a constraint 1, and minus lambda 2 g2 of x. So now we have converted our original function into a Lagrangian multiplier function, where we have lambda 1 and lambda 2 as Lagrangian multipliers, and g1 and g2 are our constraints. To solve this problem, what we did was to differentiate the function Lagrangian f of x, first with respect to x1, then x2, s1, s2, lambda 1, lambda 2. So a given function f of x, we converted into the Lagrangian form of it, and we differentiated it with respect to all the parameters or all the variables x1, x2, s1, s2, lambda 1, lambda 2. And once you differentiate them and equate it to 0, you have a set of 6 equations. And you have a set of 6 variables or unknowns. So when you solve these 6 equations, then you can find out what are the 6 variables or 6 unknowns. And based on the most feasible solution, we say that it is the optimum solution for the given function. So now let us go back to our original problem and let us try to apply the same solution for this, or the same solution method, solving method for this. So here our f of x to 2x1 plus x2, our g1 of x is 3x1 plus x2 less than or equal to 300, and the g2 of x is x1 plus x2 less than or equal to 200. So these are the constraints that we have. Now, what I can do is I can simplify or modify G1 of X. So I'm bringing 300 here, so that becomes less than or equal to 0. And my G2 of X, so minus 200 less than or equal to 0. So since G1 of X and G2 of X, both of them are less than or equal to 0, what I'm going to do is bring in a variable S1 square so that this becomes an equality. And similarly here, you can bring in a variable so that that becomes an equality. So if I rewrite that, that becomes 3x1 plus x2 minus 300 plus s1 square equals to 0. And this becomes x1 plus x2 minus 200 plus s2 square equals to 0. So these are the functions that we have now, which are G1 and G2. Now, if I apply the Lagrangian multiplier method, so this is what we need to do. So this becomes my new G1x and G2x minus lambda 2 G2 of x. So if I write this out, so f of x is 2x1 plus x2 minus lambda 1 px1 plus x2 minus 300 plus s1 square minus lambda 2 x1 plus x2 minus 200 plus s2 square. So this is our Lagrangian function. Now to solve this, we need to take a differential of L with respect to x1 first, and then differential of L with respect to x2. Similarly, we need to take a differential of L with respect to S1, differential of L with respect to S2. And we will repeat the process for lambda 1 and lambda 2 as well. So if I differentiate L with respect to x1, what I get is 2 plus, that becomes 0 minus 3 lambda, and the other terms become 0 because they are constant with respect to x, and we equate it to 0. And if I differentiate with respect to x2, then that becomes 1 minus lambda. So here in the above, we also have minus lambda 2. So here we have lambda 1 and minus lambda 2. So minus lambda and minus lambda 2 equals to 0. And if I differentiate it with respect to S1, and then we have to differentiate it with respect to S2. So if I differentiate it with respect to S1, what you get is, so the first two terms are 0, obviously, because there is no S1. This term, so the first three terms in this bracket is also 0. And what we have is minus lambda 1 S1 square. So if I differentiate that, that becomes minus 2 lambda S1 equals to 0. Similarly for S2, that becomes minus 2 lambda 2 S2 equals to 0. And now if I differentiate it with respect to lambda 1, so when I differentiate it with respect to lambda 1, all the other terms will become 0 except this. So what we would get is 3x1 plus x2 minus 300 plus s1 square equals to 0. And then if I differentiate it with respect to lambda 2, all other terms would become 0. So we get x1 minus x2 minus 200 plus s2 square equals to 0. So this is what you would get when you uh, differentiate the function L with respect to all the variables. So here we are taking the partial derivatives of all the variables. Now you can solve this by, for example, we can have 4 possible solutions in this case. And what are the 4 possible solutions? So the 4 possible solutions are based on these two differentials. So when you differentiate with respect to S1, we have lambda 1 S1 equals to 0. And when you have differentiating with respect to S2, we get lambda 2 S2 equals to 0. So what this can lead to is, from this, either lambda 1 equals to 0 or S1 equals to 0. Again, from this, lambda 2 equals to 0 or S2 equals to 0. Now, there are 4 possible combinations out of these. So one is either lambda 1 equals to 0 and let us say S2 equals to 0, or the other possible solution is S1 equals to 0 and lambda 2 equals to 0, or S1 equal to 0 and S2 equals to 0. And the fourth one is lambda equal to 0 and lambda 2 equals to 0. So these are the 4 possible combinations of solutions from the above equations, or the above 6 set of equations that we had. Now you have to test each of these combinations to find out which is the most possible solution or most feasible solution for the given function. So let us try the first one, lambda 1 equals to 0 and S2 equal to 0. So when we have lambda 1 equals to 0 and S2 equal to 0, so the first function that we had is minus 3 lambda 1 minus lambda 2 equals to 0. And the second one is minus 1 minus lambda 1 minus lambda 2 equals to 0. And then we have 3x1 plus x2 minus 300 plus s1 square equal to 0. x1 plus x2 minus 200 plus s2 square equals to 0. So when I say lambda 1 equals to 0, this becomes 2 minus lambda 2 equals to 0, meaning my lambda 2 equals to 2. So let us come back to this again later. Now here we have S2 is 0. So x1 is x2 minus 200 equal to 0. So here if lambda 2 equals to 2, and again in this scenario we are getting lambda 2 equals to 1. So this seems to be an infeasible solution because lambda 2 cannot have two values. It has to be only one value. So like this, you have to test all the four combinations, lambda 1 by considering either lambda 1 equals to 0 or S2 equals to 0 or S1 equals to 0 and lambda 2 equals to 0. So all these combinations you need to consider and solve the set of equations that we have. So this is clearly a not feasible solution because you're getting two different values for lambda 2. So if you're getting two different values for lambda 2, then obviously it cannot be a feasible solution. So if you test out all the four combinations, then you would find out which is the most feasible solution for the given function. So this is how you are going to optimize a given function and find out at what locations of x1 and x2 the function f of x is optimized. So you would get the coordinates for x1 and x2 such that f of x is optimized. Now here what we saw is when we have a function f of x that is required to be optimized, and this f of x, what we did is when we have constraints such as g of x less than or equal to 0 or g of x more than or equal to 0, we have used the Lagrangian multiplier method to solve for optimization. But we have not seen a scenario where, for example, we have f of x and the given constraint itself is an equality. So this is an equality constraint. And these are inequality constraints. Now what we saw so far are the inequality constraints when we have either g of x is less than or equal to 0 or more than or equal to 0. So now let us look at a simple problem where g of x, the given constraint itself is equal to 0. So we don't have to use the Lagrangian method. Now in that case, what we simply do is so let us look at an example. So the example is we have f of x which is minus x1 square minus x2 square, that needs to be optimized. And the constraints that we have is x1 plus x2 minus 4 equals to 0. So this is the constraint we have, and the function is minus x1 square minus x2 square equals to 0. So earlier when we had an inequality, we introduced two terms, either s1 square or s2 square. But in this case, we don't have to introduce any terms such as s1 or s2. So we simply do the Lagrangian of f of x is f of x minus lambda 1 g of x. And that becomes minus x1 square minus x2 square minus lambda 1 x1 plus x2 minus 4. So this is our L, function L. And you can differentiate L with respect to x1 and then with respect to x2. And here the variables are only 3. So differentiate with respect to lambda 1. So these are our variables x1, x2, and lambda 1. You differentiate it with respect to each of them and then equate it to 0. So let us say if I differentiate it with respect to x1, what I get is minus 2x1 and then minus lambda, that becomes 0. If I differentiate it with respect to x2, I have minus 2x2 and then I have minus lambda equals to 0. And if I differentiate with respect to lambda 1 or lambda, then that is simply minus x1 plus x2 minus 4 equals to 0. So these are the three sets of equations that we have, and we have three set of unknowns. So 2x1 plus lambda equal to 0, 2x2 plus lambda equal to 0, and then x1 plus x2 minus 4 equals to 0. So these are the three equations that we have, and you can solve these three equations and you can find out what is x1, x2, and then lambda. So here we don't have the two terms s1 and s2, and so we don't have to differentiate it with respect to that. So this is how we would optimize a given function f of x when we have constraints on it, either g of x that is less than or equal to 0, or it could be more than or equal to 0, or it could be equal to 0. Now, what we saw so far is the method that we have seen so far is optimization using calculus, because we have been using calculus to optimize the given function. Now, the next step is we are going to venture into optimization, but optimization using linear programming. So the linear programming itself, we are not going to look at in this lecture. So that we would be starting in the next lecture. But today I'm going to introduce solution by graphical method, where we are going to use the help of graph and we are going to plot the data that we have to find out the optimum solution. So for that, we are going to go back to the same example. So we are going to go back to the same example, which is about the two crops that we are talking of. So we have been talking about these two crops for almost 3 to 4 lectures now. So let us find out the solution for this. So the given data we have, as usual, converted into a form of mathematical equations. And now we are going to make use of graph to solve this. And how do we do that? So when we say graphical method, obviously we are going to construct the x-axis and y-axis for the graph. So here the x-axis is going to be x1 and the y-axis is going to be x2. And we have three functions that we need to plot. So that is 2x1 plus x2 that equals to z, 3x1 plus x2 less than or equal to 300, x1 plus x2 less than or equal to 200. Now let us start with the constraints that we have. So these are the three constraints that we have on the crops, which is x1 and x2 should always be more than or equal to 0. So at any given point, neither x1 nor x2 can be negative. So meaning we are talking about the first quadrant where x1 and x2 are always positive. So we are talking about the Q1, which is the first quadrant. So now, we have taken care of the constraint x1, x2 should be greater than or equal to 0. So that constraint is gone because we are in quadrant 1. Now x1 plus x2 less than or equal to 0. So this function, I can write it as x1 plus x2 minus 200 equals to 0. Or you can say x1 and plus x2 equals to 0, equals to 200. So this is of the form, let's say x2 equals to minus x1 plus 200. So this is of the form y equals to mx plus c, where m is the slope. So in this case, m equals to minus 1. And the intercept c is 200. So this is a line. So x2 equals to minus x1 plus 200 is a linear line with a slope of m equals to minus 1 and an intercept of 200. So we are going to plot that on the graph. So let us say this is the line x2 equals to minus x1 plus 200. So we know what is the intercept and we know the slope. So we can plot that line. Now the region that we are interested in is x1 plus x2 less than or equal to 200. So meaning we are interested in the region that falls between the axis and the line itself. So we are interested in the triangular region, this. So we are interested in all of this triangular region. So this is where our solution lies. So now we have taken care of two constraints. The first constraint is x1 and x2 should be more than or equal to 0. So we are in quadrant 1. So that is taken care of. And the second is x1 plus x2 less than or equal to 200. So we have constructed a line for x1 and x2 based on the slope and the intercept. And less than or equal to 200 means that lies between the axis and the line itself. So now we have identified a region of interest. Now let us go to the next constraint, which is 3x1 plus x2 less than or equal to 300. So this is our next constraint. Now, if I rewrite this in the form of y equals to mx plus c, then what I get is x2 equals to minus 3x1 plus 300. So my slope here is minus 3 and the intercept is 300. So now I have a new line that I can plot on this quadrant 1. So let us say I plot this line. So let us say this is my new line, which is tx1 plus x2 less than or equals to 300. And so we are interested in the region that falls below the line and between the axes. So now we have constructed the two constraints, and the possible solution may lie anywhere. So the possible solution may lie anywhere in this region that is common to both the lines. So this region in orange is common to both the line x1 plus x2 equals to 200 and 3x1 plus x2 equals to 300. So now this is the region of possible solutions. So this is our region of all the possible solutions. But there can only be one optimum solution. So although all of these points can be possible solutions for the problem or for the equation that we are trying to optimize, the optimum point can only be one. Optimum solution can only be one. And so in this case, what we need to find out is that optimum location where the function z is maximum. So what we do is again construct a new line that corresponds to 2x1 plus x2 equals to z. So this is our line z, that is 2x1 plus x2. Now let us say I equate it to some constant c1. So 2x1 plus x2 equals to some arbitrary value c1. So c1 is any arbitrary value that you can choose. And why we choose this any arbitrary value is we are trying to construct a line that represents this function 2x1 plus x2. Now you can take this c1 as any arbitrary value, and let us say if I take this as 40. Now for this given constraint or for a given constant, I have a line 2x1 plus x2 equals to 40. If I rewrite it, that becomes x2 equals to minus 2x1 plus 40. So this is again of the form y equals to mx plus c, where my slope is minus 2 and our intercept is 40. So this is our new line equation. And I'm going to plot that again here. So the red line is what constitutes 2x1 plus x2 equals to 40. So we have now constructed the two constraints that we have, which is x1 plus x2 less than or equal to 200, 3x1 plus x2 less than or equal to 300. And we have identified a region of possible solutions which can satisfy the given conditions. But we are only looking after one solution that gives us the optimum values for the function 2x1 plus x2. So to find that one optimum value, we chose an arbitrary intercept for the line 2x1 plus x2, and we plotted that line on the same graph. Now, once you plot this graph, and you can keep moving this line. So let us say I start constructing parallel lines to this line 2x1 plus x2 equals to 40. So now from this, I started constructing a set of parallel lines. And if I keep constructing a set of parallel lines, you would have one such line which coincides all the three regions. So here, both our line 1 and line 2. So this line, which is x1 plus x2 equals to 200 and 3x1 plus x2 equal to 200 are both meeting at this point P. And if I start drawing a line parallel to our Z, so this is where all the three lines would meet, and this becomes our optimum solution. And once you identify this point or the region where all the three lines meet, then from the graph, you can identify what are the coordinates of the point P, so which correspond to x1 and x2. So this gives us the optimum solution for maximizing the benefit that we want to get. And in this example, for example, if you plot this on actual scale and find out what is the coordinates for the point P, what you get is P x1, x2 would be 50 and 150. So this is our optimum solution. And what does this mean? So this means our x1 equals to 50 and x2 equals to 150. And what are x1 and x2? So x1 and x2 are the areas of crops, crop 1 and crop 2 respectively. So what we can understand is to get the maximum benefit of the crops crop 1 and crop 2, the area of crop 1 should be 50 hectares and the area of crop 2 should be 150 hectares. So this gives us the maximum benefit. And this is our solution that we are looking after. So we started with this example where we had two crops with given some constraints, and we are asked for finding the area of crop 1 and area of crop 2 such that we can optimize the benefits from the crop. And what we find from the graphical method is if we have the area of crop 1 as 50 hectares and area of crop 2 as 150 hectares, that is when we would get the highest benefits out of the cropping. So this is how we use the graphical method to solve or optimize a given function with some constraints on it. And in the next lecture, we are going to start on how to optimize a function using linear programming method. So the linear programming method is going to take us a couple of lectures. And once we finish linear programming, then we will move on to dynamic programming. And so the next plan for this week is, I'm sure you might have seen, I have uploaded a assignment on Google Classroom. So please upload your solutions for it. And if you want to discuss it with me, you can discuss with me. And there won't be any lecture tomorrow or day after tomorrow because I'm going to be on leave until Friday. So we will have the next lecture next week on Monday. The syllabus for mid-semester would be until whatever we cover in the next week. So I'm hoping we will cover at least some parts of linear programming. So the syllabus would be up to linear programming for the mid-semester. And I will also try to upload solutions for the previous tutorial and also provide you a new tutorial sheet. And the solutions for the new tutorial sheet will be available next week. So during your mid-semester exams and during the mid-semester break, since we have missed a couple of lectures due to my leave, I will try to prepare some video lectures and upload it on Google Classroom that you can watch. So that I will let you know as and when I start to plan that. And beyond that, I don't have anything for today. So if you have any questions, you can feel free to ask. Are there any questions? So as usual, the lecture notes and the reading material as well as the lecture recording will be available on Google Classroom.